Thank you very much. Thanks for the invitation. I think Gail did a wonderful job of introducing the problem of machine learning, different methods, and I appreciate that you stick to shallow models so I can talk about the deep models. However, there's a lot of commonality, and deep learning is not changing the world of machine learning, as we will see. So I will talk a little bit about the work we have done in that space, specifically applied to MR, because I guess that's the most interesting thing for you. But we'll also try to explain a little bit of the challenges we are facing by using deep learning models on medical imaging data. So just some motivation where this deep learning stuff is coming from. It's not around for a long time, at least in the medical imaging domain. And if you look at what I would call the rise of deep learning, so this is something I just updated 2 days ago by querying on PubMed the terms machine learning, whether they appear in the title or abstract of a publication. So you see this is the 2018 trend here. So this is a typical trend you see for an emerging technology, picking up on an, I would say, exponential rate. For deep learning, that looks a little bit different. So for deep learning, there wasn't really much anything before 2012. And here the 2018, and we're just half year through, is already overtaking the 2017. So we can probably expect this to rise to 2,000 publications in 2018, which is already at the level of what machine learning was gaining over maybe 15 years. So it's a bit of a disruptive technology, if we want. Although the theory and the actual methodology we are using on medical imaging is actually quite old. So the power of deep learning, as I see it, maybe intuitively or maybe naively, is coming from the following fact, I believe. If we talk about decision trees, and we just saw very nice examples of using random forests as very robust methods to avoid overfitting, for instance. But if we think about how a decision tree works, where we have these nodes where we make decisions on our data, maybe on features that we extracted on the data, and then we separate out our data. So basically a decision tree is more or less a clustering technique that you run on your training data, and in the leaves you collect statistics over your training data, which you then later use for making predictions. If you think about a decision tree, let's say just a 2-level tree where you have 2 levels of decisions and then statistics in the leaf nodes, this can be mapped to a neural network, which is basically the underlying model of all deep learning methodology. If we think about a neural network that maps exactly, or that represents exactly this type of decision tree here, what we find is that we can build a neural network with just 2 layers. So we have 2 hidden layers, and we find corresponding neurons in that network that correspond to the nodes in the decision tree. And this is fully representing this model on the left. Now, what happens if we build deeper trees? And usually when we build deeper trees, we have a little bit more expressiveness, we have more decisions to do, they become more complex, and you often get better predictions on high-dimensional data. What happens to the corresponding neural network is that it becomes wider. So each of the hidden layers gets more neurons, but the depth of the network doesn't change. So you still have a 2 hidden layer neural network that represents any depth of a decision tree. Now the power of deep learning is that we are not limiting ourselves to just 2 hidden layers, but we use many hidden layers. And that's where the term deep comes from. When exactly are you starting to call it a deep network? That's debatable, but usually you do have a number of hidden layers. And the power here is now, if you think of each of those nodes being a decision function that is applied on your data, you now have many, many more of those decision functions. And the interesting thing is, the deeper you move into your network, the decision functions are applied on previous outputs of a previous decision function. So what you're starting to do is, by having lots of those layers, is you start to learn features of features of features of features, which is different to the shallow models, which are usually just taking in a combination or some predefined set of features initially. Here we're actually learning combinations of outputs of consecutive feature learners. So if you want, to think about the previous talk and think about models like SVMs, for instance, or logistic regression. Now think of each of those gray circles here as being one linear model or one SVM. So you see the power in deep learning is that you actually now combine maybe millions of SVMs in one single model. So people and us as well started to use these type of neural networks for medical imaging. We started using convolutional neural networks, which are one particular example of a neural network using convolutional filters. So each of those gray circles that you saw before is now a filter kernel. It's a filter that is applied to initially to the raw input data. So let's say we have an MRI brain here, and we want to predict for each voxel whether it's part of a lesion. Then these convolutional filters are applied on top of each other, and each of those layers here is learning a different feature map, or or multiple feature maps that are then combined. And at the end, you have again something very simple like a linear classifier that takes the output of the last layers, combines everything, and makes a final prediction. So in this particular model, which we call DeepMedic, we specifically targeted MRI brain data. So we tried to incorporate some of the information that we had from previous models, like using random forest, that it's very important to incorporate context. So this model has two pathways. One of them is looking at the image at the highest resolution, at the native resolution, and the other low resolution pathway is looking at this same image but in a downsampled or resampled way, so it can also capture context. We find this is quite important. For instance, if you want to predict lesions, you not only want to know very specifically at a local position, is this feature discriminated to say whether it's part of the lesion, you also want to learn where you are in the brain, so spatial location is quite important, and this lower resolution pathway allows you to do that. So we applied this to many different tasks, in particular brain lesions, which was one of the first things that we looked at when we started to use deep learning methods. And the reason why we now completely moved towards deep learning for these type of tasks is that we basically consistently saw that on all benchmarks, on all problems we were previously maybe running random forests, is that deep learning just gives you a big margin in improvement. Now, I'm not talking about a 0.5 improvement, but really like significant improvement here in terms of deep learning methods. However, if you compare different deep learning models, and there I have to completely agree with Gael, then it becomes less clear often where an improvement currently is happening. Anyhow, so we applied this on different problems like traumatic brain injury. This is one collaboration we have with the Edinburgh Hospital in Cambridge. We applied it on stroke data. What is interesting to see is, so this particular model that we proposed here, DeepMedic, is able to do well on different types of lesions. So smaller lesions that are scattered around the brain. For instance, in TBI you have microbleeds that you see only in things like the gradient echo scan. It's able to recover those, but also the big contusions. So it's a model that deals well with these heterogeneous types of lesions. What is interesting is when you talk about machine learning in general is because you usually train from some manually annotated data, which is usually expert annotation. So you have radiologists maybe sitting down and doing a lot of manual drawings. Is that you kind of face this problem at some point on evaluating whether you do well or not. In particular, if your annotations are not 100% trustworthy, if you wouldn't call them ground truth. Obviously, they do have errors. Manual annotations always contain errors, but there are also ambiguities. They might be imperfect by nature. What we do see is, for instance, when we compared the results on traumatic brain injury, where we wanted to see, first of all, how well does it do in terms of DICE score, which is an overlap measure for segmentation tasks, but also, more importantly, for instance, to predict the lesion load, so the volume of the lesions in the brain, which is an important predictive marker, prognostic marker. We saw, for instance, in this case, where we had 60 patients at test time, where we looked at the comparison between automatic and manual segmentation, that we had two extreme outliers, where we once completely underestimated and once overestimated the lesion volume, and then we went back to the data And the clinical experts clearly said the manual annotations were wrong there. So if you do this comparison to manual annotations, you're always facing this problem of, do you really want to match it 100%? Or when do you start to believe that the machine is maybe even better than the manual ones? How do you evaluate that? It's, I guess, an ongoing struggle in using machine learning techniques. This is very recent work. So after we saw that this works well with lesions, so pathology prediction in brain MRI, we wanted to look what else can you do with these deep learning models. So we do see that if you have large enough training data, and that was mentioned, more is better, you kind of see that those models work really well in replicating what you put in. So they are extremely good in replicating the annotations that you put in. So we tried this and we built something that we call NeuroNet, which is a neural network that takes a brain MRI and produces structural segmentation. So it currently takes a T1 weighted brain MRI. It has a neural network that first learns the features, and then it has an output, and it can predict the structural segmentation of what you feed in. Now, where do you get your training data? So one idea we here had is that neuroimaging is quite advanced in terms of providing state-of-the-art tools. So there's FSL, there's SPM, there are other well-established techniques for automated segmentation of the brain, and people use it to do large-scale neuroimaging studies. So what if we just trust those tools and we run them on large amounts of data and we train a deep neural network that replicates just those tools? What would be the advantage is that, first of all, it will be much more it will be faster at test time when you run it on a new case. We can actually do multi-output. So in this case, we're basically with a single network, given a brain MRI, predicting SPM, FSL, and all the others simultaneously. So you're not faced with that problem of choosing for your study which tool to use, and you know that you will introduce some sort of bias. You can actually maybe use all of them. The hope would be that they also help each other, right? So if you try to predict tissue maps, gray matter, white matter, and CSF, produced from 3 different automated tools, there might be a variation. And since you train on all of them, you might benefit from averaging out some errors. So that would be kind of the hope. It's hard to show, but that was the motivation for it. The other advantage is that here we are basically training within the network. We're learning the whole pre-processing pipeline. So normally you would have to do skull stripping, bias field correction, all these steps before you maybe give it to a segmentation tool. Here we started from the raw brain T1 weighted MRI, and basically learned the whole pre-processing within the network itself. So you really now give it a raw brain MRI and you get all these outputs. So we trained this on 5,000 scans, which we got from the UKBB, where also the automated segmentation has been quality controlled by the people who did this. As I said, we didn't apply any pre-processing like the typical brain extraction and so on. And per scan, it really just takes 90 seconds for a full 3D volume to get all these different outputs. So these are the DICE scores where you compare how well you replicate the original input. Now, keeping in mind that those numbers are quite good in terms of replicating, but they are not perfect. But the question again is, do you want to be perfect? Do we want to replicate perfectly what FSL gives us as an input? Or if we follow this intuition that maybe because we trained on FSL, SPM, and others at the same time, maybe we get better. So obviously we'll be worse in compared to replicating what we originally put in. We also saw that it becomes a little bit more robust. So sometimes SPM can fail, maybe due to bad orientation of the scan, and we saw that our NeuroNet does well even if the image is not like pre-registered to MNI or similar. These are just some visual results. The NeuroNet is available online, so if you search for DLTK, you find the source code and the trained models for that. We use this for other applications, so cardiac imaging is another application area. Again, on what we would call a relatively large data set, so 4,000, almost 5,000 subjects, again taken from the UK Biobank imaging study. So we could do a reasonable training, validation, and test set, as we saw earlier. This is quite important to keep the test completely separate from your method development stage. And again, this is just an example of that deep learning methods do work reasonably well. So we have some numbers on DICE, how well we can segment left ventricular cavity and so on, maybe showing you some visual results. So there's one example. So this is basically a 4D scan that we segment here. More interestingly, going back to the question, how do we evaluate now whether something like this is good? You do not often need to do a pretty tedious and painful job by actually getting multiple experts in. So here what we did is on a subset, because doing it on all 600 test cases was not feasible, but on a subset we had 3 experts doing the full task of manual segmentation, and then we can compare what the automated version is compared to all of those experts. And the nice thing is we can also compute the variability between experts. So maybe what is interesting to take home here is that if we look at the difference between what the automated deep learning approach does compared to what we would call the best manual, maybe the consensus manual segmentation, it is within the ballpark of variability between experts. And I guess that's really as much as you can hope, because then you would basically have another expert, but now you have an automated one. We apply this to other applications. So this is just an example from whole body imaging, a project that we're currently doing on cancer. So the idea is to find lesions in whole body scans. And towards that, one of the tasks is to first do multi-organ segmentation, so trying to find the major organs, which then later on will give us very useful priors about where we are in the body when we try to identify whether a suspicious region is really suspicious or just has similar characteristics as maybe a normal structure, like the spleen, for instance, does show up in diffusion MRI, very similar to cancerous lesions. What we do see here is that there are obvious limitations. So another deep learning approach here applied to the multi-organ problem shows very good segmentation results for major organs, so liver, lungs, heart, kidneys. You can do all reasonably well, while the same model struggles pretty much with smaller organs and also variable organs like the pancreas. So there's certainly still space for improvement. These are, again, just visual results on a set of those whole body scans. Now, this was kind of an idea of giving you a little bit of a flavor of where deep learning is already successful, I would say, in medical image analysis. It's mostly segmentation task at the moment where we see a lot of improvement by moving towards these deep models. However, there are challenges. One of the biggest challenges, I believe, is robustness. We do see dramatic performance drops when the input data changes, and this goes back to the question of how heterogeneous, how homogeneous should your data be. We saw across, so there are these challenges, these benchmarks where people can contribute with their algorithms. So the MICAI community is very good in that, organizing these public challenges. So for instance, we saw an example from Kaggle, where people compare their algorithms with each other on data that is given. And what we saw so most organizers were very clever over the last years by holding out test data from different sites. So the training data was kind of giving you a good variability, different sites and so on, but then the test data came from a different hospital, different scanner. And all the models that performed really well in the challenges all had dramatic drops in performance when they were exposed to data that they really have never seen before. And the interesting thing is different models behave slightly differently. So when you talk about deep learning or neural network, there's a lot of talk about architectures. So people come up with different ideas of basically putting building blocks together, and then they give the architecture a name, and then they write a paper. But basically it leaves us with like lots of choices. And one of the problems is really this agony of choice. If you go into deep learning now, and unfortunately there is not something like scikit-learn where we can just like trust that people have really put a lot of thought in making these methods state-of-the-art and they work really well. There are, of course, deep learning toolkits, and all of them are slightly different. But as a non-expert, I would think it's still very, very hard to use them, especially if you want to apply them to your own data that maybe nobody has done before. I think that's different with the shallow models. They are easier to transfer to new problems. So as a developer, we often faced with this agony of choice. So people come to us and say, here's my clinical data, can you solve my clinical problem? And we start to look at this list, and we probably choose a model by more or less randomly, or maybe from some experience, picking some of those things. We pick an architecture, we pick a loss function, we pick a sampling strategy, but all these things will obviously influence your performance. And they will influence the bias you have, the variance, and so on. So one simple thing there is going back to like ensembles that we have seen earlier for decision trees. You can apply the same strategy to deep learning. It's a bit more cumbersome because each like model like needs a proper workstation, runs for a few days, so maybe it's not as straightforward of running these ensembles as for things like random forest, but you can do that. So we dubbed this EMMA, ensembles of multiple models and architectures, where we basically threw in all the models we knew. We had deepmatic implementations, we have fully convolutional networks in our DLTK, we have other people's code on UNets, and so these are different flavors of neural network architectures, CNNs. We basically trained all of them, and with different inputs and so on. And then we used this to participate in the last year's MICAI Brain Tumor Segmentation Challenge, and maybe not too surprising, it performed best over all participating teams. So I'm just showing you some visual results here. You can look up the numbers on the website. So this is a result, and I'm just showing you now. So I hope you do notice that there is another image coming every time I click, which is actually the going from the automatic one to the manual one, automatic one, manual one. So this model really works well on this task of brain tumor segmentation. It currently performs best of all the models, and if you want, an ensemble is a bit of a cheat, because whenever someone comes up with a new model and says, this is now a better model than before, we just put it into the ensemble, and again, the ensemble should work a little bit better. So this is future safe, I guess. And as I said, so image segmentation was really, I think, one of the driving applications in medical imaging for these deep learning models. However, of course, there are other applications. So we look currently a little bit into abnormality detection. I mentioned this on whole body MR, where we try to find what are the tumorous lesions, what are normal structures that do kind of look similar. Again, spatial context, very important to incorporate. Imaging biomarkers is, of course, a field where once you have reliable, robust automatic segmentation, you can do interesting things across different types of lesions, across different modalities, maybe here CT and MR, extracting information about organs on different modalities, maybe even about different organs, so doing brain together with cardiac analysis, I guess is very interesting in certain population diseases like high blood pressure. These deep learning methods, or previously other machine learning methods, are also used actually to generate the images itself. So there's a lot of interest in using it for MR image reconstruction by doing undersampling in K-space. This is just an example from one paper. It's all a little bit biased towards what we have done in the past. Of course, other people do very similar similar applications. So this is just an example of like a ground truth, fully sampled MR and a reconstructed MR using a machine learning technique from an image that would naively just look like this. Similar things can be done on super resolution. I know upsampling of medical images is a debatable topic, and people have different opinions about this. But we do find that it can help to, for instance, have clinical cardiac scans of low out-of-plane resolution, upsample them with a learned upsampling, again from a CNN, which looks better than just doing naive linear interpolation, for instance, and that can help for downstream tasks. It's probably not an image that you would use for diagnosis, but you might use it for doing quantitative measurements like left ventricular volume. There are lots of other applications, you can name them. Population imaging is of course interesting. If you do have models that don't take 2 hours, but just 90 seconds on an image, it's more feasible to run them on 100,000 scans, right? So, and the UK Biobank is one example that I mentioned. There are other studies that go towards that scale. So the UK Biobank is currently at 20,000 scans. They will reach 100,000 in 3 years' time. And someone needs to extract quantitative information from those images reliably. Which brings me to my last part, which is the pitfalls. And I know there is, I think in 3 talks from now, a talk about pitfalls in machine learning, which probably connects, hopefully, very well to this problem of learning the right features. So I just have this conceptual thing here to start with, which is if we think about the training data, that obviously defines what type of features we will learn. Now, if we are given training data from a site A, let's say a hospital close by, and they give us this data and they have done manual annotations of what's malignant and benign, a deep learning approach where you don't control what features are used, remember you feed in the raw data and then in the layers you learn what's used for making your prediction, we'll probably learn that color is a pretty good feature here. However, it will then, when you give it test data from a new site, completely fail, right? Because color was not the feature that it should look for. It will never look for shape in the first place on training A, on training coming from site A, because you didn't tell it to. So you only said minimize loss function, and the loss function is minimized perfectly when you go for color. So it will always pick the simplest feature that's available in the data. That's a little bit the pitfall of automatically learning features. If your data at the end is not representative, then you will learn the wrong features. There's an issue about variability in data. Gail made the point of saying we love heterogeneous data, that's what we want to work with. Unfortunately, most of the time, that's not what we're given when we do the method development. I believe a lot of papers, and I have to include ourselves, that do report numbers will probably work on a limited data set where we have our annotation, they have been maybe collected from one side, and the data more or less looks like this. However, once you move to clinical applications, probably your data looks much more like this, or the interesting data looks much more like this, right? Where you would like to make predictions. And this model will fail if it's trained on data coming from the left side. So it's good to think about the data in the first place before you actually start even doing machine learning. Just to give you maybe a primer, so I did run a little experiment just for this event, where I looked at some multi-site data. And for this, I took 3 Tesla T1 weighted brain MRI from 2 studies that I had access to. One is the CAMCAN study, which studies aging, and one is the UK Biobank. Now, CAMCAN has this whole life range, age from 18 to 80. UK Biobank doesn't have that. It only has scans, I think, from people starting at age 40. So what I tried to do, so looking at the scanning parameters, for me as a non-expert in MRI, they kind of looked similar. So at least it was a 3 Tesla scan, looked good. It was a Siemens scanner, same manufacturer. They had similar head coils. And then about the other numbers, I can't say much. You might know this much better. But what we then tried to do is to create the perfect data set of a multi-site study that I guess everyone would love to have, which is age-matched and sex-matched. I don't know what else you can match by just having a little bit of demographics and your MR scans, but I kind of felt that that is probably the best you can have when you want to compare data from different studies. So I ended up with 618 scans, 309 per site. And then I applied typical neuroimaging pre-processing steps like skull stripping, bias field correction, all what I would say is state-of-the-art or what you would find in a neuroimage paper. I did linear registration to MRI and so on. So this is just some examples of the data. After I did pre-processing, I look at the intensity histograms here, and to me it wasn't obvious visually what the differences are between CAMCAN and UK Biobank. So here you always have matching subjects in terms of sex and age. And then I did the first simple thing is I trained a binary classifier to tell me where the data is coming from, right? Because I wanted to see if variation is left in the data according to where the data is coming from. And not surprisingly, if you, for instance, don't do bias field correction is very scanner specific, you get these very high accuracies in telling you where the data is coming from. And I applied different types of intensity pre-processing. So these are typical things that currently deep learning people would do. Whitening, zero mean standard deviation, range matching, and so on. And then I looked at different, so let's go to this field where we have bias field corrected data. What is interesting is that you do reduce a little bit the accuracy of where the data is coming from for a classifier. It's still very high, right? but the entropy goes up, average probability goes down a little bit. When you look at registration, in terms of actually removing spatial variation like affine or even nonlinear registration, you even increase the accuracy of the site classifier. So the registration is encoding again something that is site-specific. What's also interesting is that this happens after you have run, for instance, a pre-processing state-of-the-art pipeline like SPM, white matter, extraction, and so on. You still have very high accuracies. Now, what this can lead to, and I have to finish here, is that if you train on the wrong data, where sex classification should lead to 80% accuracy, if you do it on biased data, you might get wrong predictions. So this is what leads me to the end. I hope I gave you a little bit of an idea what deep learning can already do, but also what the current pitfalls and shortcomings can be. Thank you very much.